But 3.2, modeling a gas. So we've been talking about heat and energy and temperature and things like that. Now we're going to look at how it applies to gases. What's the essential idea say? Anyone? Okay, cool. So we're going to talk a lot about this thing called the ideal gas law. And one of the things you have to recognize is the ideal gas law is that. It is, in fact, that. It is ideal. It is not real. Real gases don't always behave this way, but in a perfectly ideal situation, this is what we're going to get. So we'll deal with it. Pressure, equation of state, kinetic model. And notice there are a few equations, 1, 2, 3, 4 equations. So, cool. There you go. Now, some of this is kind of review. Difference between temperature and heat. Difference between temperature and heat. Temperature is? Great. A measurement of the average kinetic energy of the molecules of a substance. And what is heat? Due to? Great. Heat is a transfer of energy due to a difference in temperature. What's heat measured in? Joules, because it's energy. What's temperature measured in? Celsius or Kelvin. Good. Awesome. So, understand the difference between that. It's always a good thing. Sparklers are a great example. Sparklers, you know the sparklers, little things used on the 4th of July, or, you know, right? They have extremely high temperatures. Those little sparks that come flying off are like thousands of degrees hot. They're really hot. They have incredible amounts of kinetic energy. However, they don't have very much heat because they're so small. Their mass is so small. That's why they don't burn you very much. So there's a difference between temperature and heat. Okay? All right. Heat and temperature are just forms of internal energy, right? That are either transferred or at rest, and they must obey the laws of conservation of energy, which is how we solved a lot of the problems that we did before. We did the ball in the ring demo, so I'm not going to do that again, right? We talked about expansion, things heat when expanded. Most things expand when heated, I should say, not heat when expanded. So, right, most things get longer or larger when they get heated. That's not true necessarily for water. We talked about a lot of this. Your gas tank expansion joints and bridges, remember that, right? Bridges, as they change temperature, are going to get longer and shorter. So if you built them as a solid entity, they would buckle and get all weird as temperature changed. So most bridges have these things called expansion joints, where it's designed so they can get longer and shorter without destroying the bridge. All good? Okay. Water, we said, is the oddball. Water actually gets more dense. It actually contracts from 0 to 4 degrees, and then it starts expanding again from 4 above. Just a strange thing. Density of water is greatest at 4 degrees. Okay. This is the beginning of topic 3.2. You ready? You guys ready? Here we go, pressure. Pressure. Have you ever measured pressure in a tire before, like a bike tire or a car tire? And what is that? What do we measure it in? What do you measure that pressure in? PSI, pounds per square inch. Awesome. Pounds are a unit of, which is a force. Good. So pounds are force. Square inch, what's that a unit of? Area. So pressure is the amount of force exerted over an area. It's the force per unit area is what pressure is, okay? The amount of force that something exerts per unit area. The equation, this is the first one in the unit, P equals F over A. Pretty simple. So what will the units for pressure be? Force, newtons per, great, newtons per square meter. That would be the units. Now we give it a new name. A newton of force, which is about the weight of an apple, spread over an entire square meter is equal to 1 Pascal. Is that a lot of force or a little bit of force? If I'm like, ooh, I'm going to exert a Pascal of force on you, are you worried? The weight of an apple spread over a square meter? Not very much. It's not a very large unit of force, okay? You are experiencing a huge amount of force on your body at all times right now, however, because the atmosphere, which has weight, is pushing on you. It's exerting force on you in all directions, the weight of the hundreds of miles of atmosphere above you, and we call that pressure 1 atmosphere. And 1 atmosphere is equal to 1.013 times 10 to the 5th pascals, 101 kilopascals. Write that number down for some of your homework problems. It is not something you will need to know on a test unless it's given to you. Just recognize that sometimes people talk about pressure in atmospheres. In IB, you'll almost always look at pressure in pascals, or more commonly probably kilopascals. Now, 1 atmosphere of pressure, this weight, this pressure that the atmosphere is exerting on you is equal to almost 15 pounds on every square inch of your body. 15 pounds of force is pushing on every square inch of your body. That equates to thousands of pounds of pressure on your body that you've never noticed because you've lived in it all your life, and your body is designed to deal with it. If I took that pressure away from you, you would die. If I increased that pressure extensively, you would die. But we like it. It's kind of perfect. We like it. So let's do a little demo. So we did the little suction cup demo just to give you a feel for pressure. So what IB wants you to understand about pressure, one is the force per unit area, but also on a molecular level, what's exerting pressure? If you've got 14 pounds per square inch pushing on your body right now, what's doing the pushing? More specifically? Yeah, that's what's in the air. Yeah, but what is air? What is air? Molecules. It's actually the molecules themselves that are exerting forces. How in the heck are these tiny little minuscule molecules exerting forces on you? And what are they doing? And what are they doing to exert a force? No, you're not there yet. Are they standing still? No, because why? They have temperature, right? Which means they have kinetic energy. So what are they doing? Yeah, and what are they doing to you to exert forces on you? Thing that is creating pressure are collisions, molecular collisions with you or with a container wall. That's what makes pressure happen. So please be aware of that pressure results from the collisions of molecules with a surface, not with each other. The molecules are colliding with each other as well, but that's not pressure. The pressure is when they hit something that is a surface and they bounce off of it. That exerts a force on that surface, okay? The container could be you, for example. The change in momentum when the molecules change direction means that there was a force exerted on them. If there was a force exerted on the molecules, then Newton's third law says, hey, those molecules also exerted an equal opposite force on the container wall. So, if this is what creates pressure, how can you change the pressure in a container? Add more molecules so there's more collisions. Make the container smaller so the collisions happen more frequently. Or, which does what? So that there will be more collisions per second. Good. And they'll also be moving faster and exert more force when they collide. So those are all things that you can do. You can have more collisions or greater speed with the collision, and that will change the pressure. Good so far? Okie dokie. Let's try an IB question. You guys need to see this? Maxine, you good? Okay. Here's an IB question for you. Take a look at it. If you're at home, hit pause. See what you can think. See what you can do. Okay, so let's take a look at it. Is one a true statement? Yes, that is true, because, by the way, so wait, constant temperature. What does that tell you about the molecules if it's constant temperature? They're not changing their average speed. The average kinetic energy is staying the same, so overall the speed's staying the same. So why will there be more collisions with the piston if they're not moving any faster? Less space. Good. Smaller area. Good. Smaller volume. Good. Is 2 a true statement? The average. Okay, so that's just not even a true statement. Good, because the temperature is constant, right? How about 3? Is that a true statement? Great. Now, of 1 and 3, which one actually deals with pressure? Just one. Just one. 3 is not an untrue statement. 3 is a true statement. However, when the molecules collide with each other, that's not exerting pressure. That's just collisions with each other. The thing that exerts pressure is when molecules collide with the container surface, the container wall. I always think of a balloon in this unit, right? The thing that exerts pressure on that balloon is the molecules colliding with the balloon. Okay? Good? All right, which leads us to the kinetic theory of gases. Now, this is a theory that explains how gases behave using physics. It makes a ton of assumptions. You will see this list again in your textbook. You need to know some of these assumptions. IB will frequently ask you to list what are some of the assumptions of this theory, okay? I don't expect you to memorize them all, but you should know some of these. And it is a mechanical model that explains gas behavior using physics, using mechanics, but here are some of the assumptions it makes. One, that a gas consists of a huge number of molecules. That seems reasonable to me. Most gases do consist of that, okay? The molecules of a gas move with a variety of speeds. I think that's a reasonable assumption. The volume of the molecules is negligible compared to the volume of the gas itself. So molecules are incredibly tiny. Seems reasonable. These are pretty reasonable assumptions. Every time a molecule collides with itself or with another molecule or with a container, every one of those collisions is truly elastic. I don't know if that's a good assumption or not because I can't see molecules, but what makes a collision elastic? Great. Kinetic energy is conserved in that collision. Good. That's what makes it elastic. So that's an assumption we make with these gas laws. Another assumption that is, I don't know if that's necessarily correct or not, but molecules exert no forces on each other or the container except for when they collide, which means there's no potential energy between those molecules because they're so far apart. The assumption is that they're not exerting electrical forces on each other. They're not exerting gravitational forces on each other. The only time they exert forces is when they actually collide. I'm not sure that's a correct assumption, but it's an assumption made for this model. The duration of the collisions is very small compared with the time between collisions. That seems not unreasonable. And finally, we assume that molecules obey Newton's laws of mechanics. So in order for this mechanical model of gases to work, you have to make all of these assumptions. And again, I don't expect you to memorize all of these, but you should know a few of them. It's a common question for IB to say, what are some of the assumptions that are made in order for this gas law to work? So now we're going to move into this mechanical model. People in the 1600s and 1700s, there were a number of scientists that started exploring the behaviors of gases. And the main three characteristics they looked at were, actually there's four characteristics that were looked at: pressure, volume, temperature, and number of molecules. Pressure, volume, temperature, number of molecules. And initially, people looked at these all independently. And the first person that's given credit for doing this is Robert Boyle. Now, you'll see in the video that I asked you to watch for homework that this guy actually didn't come up with this idea. He stole it from a few other people, but he's the one that got credit for it. And that's just the way science and life works sometimes. So, what Boyle discovered, this is known as Boyle's law, he discovered that the volume of a gas is inversely proportional to pressure when the temperature is kept constant. So mathematically, P times V is a constant for a gas if you keep it at a constant temperature. And I think these laws are somewhat intuitive if you think about them. If you think about a balloon filled with gas, and if I keep the temperature the same and I just make the balloon smaller, the pressure is going to go up. If I make the balloon bigger, the pressure is going to go down, and vice versa. If I increase the pressure, well, no, see, that makes more sense to me if I change the volume first. So for Boyle's law, we would get a graph that looks something like this. Okay, that's the inverse relationship. One gets smaller, the other gets bigger. And it's not linear, it's going to be kind of an exponential relationship. In the 1700s, this guy Jacques Charles comes along. Okay, this is after Boyle discovered the PV relationship. And he discovers a relationship between volume and temperature, given a constant pressure. And he says, hey, they are directly proportional. Or V divided by T will be constant if pressure is kept constant. Okay, so in this case, if I want my pressure to stay constant and I heat the gas up, the volume has to get bigger. If I cool my gas down, the volume has to get smaller in order for the pressure to stay the same. That's basically what Charles is telling us. Okay? So here's a graph of Boyle's law. Let's look at Charles's law. He says, hey, for a constant pressure, if I look at temperature and volume, I now have a linear relationship. Now this is where it gets kind of funky. It's a linear relationship, right? It does start at the origin sometimes, but not always. So check this out. Let's think about what this potentially means. So if it doesn't start at the origin, this is a really important point. What has happened at that point? Temperature's negative. What's happened to volume? 0. Now that's kind of weird. How can you take a gas made of molecules that have volume and cool it down to a point where the volume vanishes? Well, obviously you can't do that, but if you could, what would that temperature be called? There's absolute 0. Now, if your temperature is in degrees Celsius, what's that intercept going to be? Negative 273. Good. What would you have to change so that this line went through the origin? Kelvin. Good. If your scale is in Kelvin, then this line does start at the origin. Does that make sense? Okay. Cool. So really, this is how the concept of absolute 0 first came about. Like, oh, if I get a gas cooler and the volume decreases, there should be a temperature at which the volume goes to 0. That's weird. That you can't go negative volume. You definitely can't even get 0 volume. So we're going to call that absolute 0. That is the limit of temperature. Absolute 0 graph. Okay. Then this third guy comes along, and again, all three of these guys are just discovering pieces of a much bigger law. This is in the 1700s. He looked at the relationship between pressure and temperature and found that it was linear if volume is kept constant. And that makes sense too. If you have a hard container and you heat the gas up inside of it, you would expect the pressure to go up, right? Or if you cool it down, the pressure goes down. So that's the relationship between pressure and temperature. And again, we can get absolute 0 this way as well. It would be the temperature at which pressure became 0 on this graph. Okay? We're going to combine all three of these into a beautiful, beautiful law known as the ideal gas law. IB question for you. Let's see how you do. I expect 100% on this one. Here we go. Okay, so we just looked at this a second ago. The correct and true answer is A. It is A, right? Because we're reading in Celsius. B would be true if this was what? Temperature in Kelvin. Good, good. Okay. Similar. So these three guys, again, were making discoveries around the periphery of this much bigger relationship that we now call the ideal gas law, and this you definitely need to know. It's in your data booklet. Get comfortable with it. Wrap your arms around it. Embrace it. PV equals nRT. It relates 4 qualities of gases to one another: the pressure, the volume, the number of molecules, and the temperature. Great. So lowercase n, what does that represent in this equation? Lowercase n, the number of molecules? Or how do we represent the number of molecules? Is it actual number of molecules? Number of moles. Please remember that. That will be critical for you in this problem. If you use number of molecules, you will get incorrect answers. It is the number of moles of the molecules. R is a constant. It's known as the universal gas constant. It's in your data booklet. You don't have to memorize it. 8.31 is what it equates to when you're dealing with moles, when you're dealing with pascals, cubic meters, and Kelvin. Okay. Volume is V is volume, and it's measured in cubic meters in IB physics. If you took chemistry, you might have measured volume in liters. If you're doing home, yeah, I'd say don't even worry too much about this a little bit. These are the things that we're going to be dealing with in physics mostly, is cubic meters for volume, pascals for pressure. Okay. Maybe I should explain this just in case. I don't know if it's more confusing or not to explain it to you. Yeah, that's the units for it. It's weird because of the cubic meters and the pascals. Since a pascal is a Newton per square meter, you end up getting joules that way. That's kind of how it works out. Okay. And then pressure is measured in pascals. Okay. And remember that 1 atmosphere is 101.3 kPa. Again, that's not something that IB on an exam would ask you, but for homework you might need to know that. Okay. So here we have this beautiful relationship between pressure, volume, number of molecules, and temperature. Key thing that oftentimes you might forget is that temperature, I didn't even put that on here, temperature has to be in Kelvin. Celsius will do you no good with this law because it's not delta T, it is T, so you must be using Kelvin, especially since you're using a constant who only works in Kelvin, okay? Temperature has to be in Kelvin. Remember that. Remember that. Remember that, okay? Now, why do we call this the ideal gas law? Seems like it would be a great law. It's an ideal law. When actually it's not that ideal. It actually doesn't work in a lot of scenarios. So that's why it's called an ideal gas law. It only works ideally. It only works on an ideal gas. So one of the things that IB wants you to know, and they often ask you this, is what makes something an ideal gas? And an ideal gas is a gas that obeys the ideal gas law at all temperatures, all volumes, all pressures. Real gases don't do that. We talked about it earlier. If you increase the pressure on a real gas, it'll eventually become a liquid. And so the gas law fails then once it liquefies, right? If you get the temperature really low on a gas, it will also liquefy. Then the gas law is all screwed, it doesn't work. So the ideal gas law only works on real gases at very specific ranges of temperatures and pressures. So if IB says, hey, what makes something an ideal gas? Please just say, oh, an ideal gas would be a gas that obeys the gas law at all temperatures and pressures, okay? Real gases don't do that. Real gases actually obey the gas law at low densities, okay? Which means basically at low pressures and at relatively high temperatures, relative to absolute zero, okay? These are two things that you get asked a lot when you're dealing with gases in IB stuff. You'll solve problems with the gas law, and then they'll probably ask you something about this. What makes a gas ideal, or when does the ideal gas law work on real gases? All right, let's practice. This is an IB question. So you got a mole of an ideal monatomic gas. What does monatomic mean? One type of atom, which means they all have this, same masses. Trapped in a cylinder, volume, pressure. This is a 5-point question and broken into thirds. So state how the internal energy of an ideal gas differs from that of a real gas. Determine in Kelvin the temperature of the gas in the cylinder. And 3, the kinetic theory of ideal gases is one example of a scientific model. Identify 2 reasons why scientists find such models useful. So number 2 is the easiest one. It's exactly what we just talked about, plugging and chugging into the equation. Numbers 1 and 3, you're going to have to think about those a little bit harder. And I encourage you to talk to each other, and then we will go through it. Okay, so I think number 2 is the one that we've been talking about, PV equals nRT. What'd you get for temperature? 7.7 Kelvin. Perfect. And that's worth 2 points. Now, here's the crazy thing about IB I just want you to see. So you know the equation is PV equals nRT, right? Well, if you got 7.7 Kelvin, you're pretty good, and I think you get full points for that question. However, if for some reason you did incorrect math and you didn't get 7.7, IB would not give you credit for writing this. They'd want to see you write this, but then they'd want to see you solve for T and say, oh, well, that's PV over NR. This gets you a point regardless of your answer. Does that make sense? This does not give you a point. So just be aware that when IB asks you to do some math, write the equation, manipulate the equation for the variable you're solving for, then plug in numbers and do your math. Okay? Awesome. Anybody have any ideas about number 1? Number 1. How is the internal energy of an ideal gas different than that of a real gas? Tell me again what internal energy is. The sum total of the kinetic and the potential. Great. And what was one of the assumptions we made about the potential energy of the molecules in an ideal gas? Or the forces they exert on each other when they're just flying around as a gas? That's the collisions, good. But what about when they're not colliding? Do they exert forces? No. So that means they exert no potential energy on one. There is no potential energy in an ideal gas, which is kind of weird. That doesn't really seem to fit with reality, okay? So that's what they were looking for. Intermolecular potential energy of an ideal gas is 0, or is negligible, okay? Whereas in a real gas, that's not true. Number 3, why do scientists find such models useful, you guys? Any models. The ideal gas is a model of how gases behave. There's other models. There's the models of the atom. There's I can't think of any others right now. There's a ton of other models. Why do we use models? He said, I like the idea of allowing simplified thinking. What they are saying is it allows you to predict or hypothesize or lead to further theories. The response needs to identify 2 different reasons. Actually, if you're SL, you only need to do 1 different reason. So, which they also help you explain, help you understand, help you visualize. Okay? That's why we use models, is because they allow us to gain an explanation or understanding of something that's so complicated that otherwise we may not be able to. So when we talk about climate change, for example, people make models of the atmosphere and how they work, because the atmosphere is so complex, it's a hard thing to fully grasp, but you have models that help you. They also allow you to do simulations, simplify, approximate. Those are the kinds of things we're looking for. That third question, you guys, is a new thing that IB Physics is doing, where they call it the nature of science, and they will ask you questions about the nature of science. This is a nature of science question. Why do scientists use models to help make predictions about things? Now, finally, what I want you to see, actually, it's not finally, there's like 1 or 2 more things I want to talk about, but the ideal gas law sometimes can just be used as a ratio. So rather than solving for a specific variable and plugging it into PV equals nRT, sometimes you'll have a state of conditions before, in an initial state, you'll have pressures and volume and number of gas. Oftentimes, the number of molecules stays constant in these types of questions. And then you can compare them to a second state, where we let's say they give you a gas at a certain pressure, volume, and temperature, and then they say the pressure does this, the volume does this, what's the new temperature? And you can just use a ratio, kind of nice. Can you see why this ratio works? What is PV over NT equal to? PV over NT, what does that equal to? It's equal to R, which is a constant, the gas constant, right? So that relationship on any gas should be the same value, okay? All right, take a look at this one. So this is where we can deal with that ratio just a little bit. Okay, let's walk through this one a little bit, you guys. So first thing, we got to do a ratio of pressures. So we'll deal with, what's the equation we want to work with? Sure, PV equals nRT. And whenever you guys do, oh, that's PV equals nRT. Whenever you're doing the ratios, solve for the variable that the ratios are about, which in this case is P. So P equals nRT over V, right? So then I'm going to do nRT over V for X compared to nRT over V for Y. Are any of the things the same? R is the same and V is the same? How do you know V is the same? Okay, identical boxes. The size of the box doesn't change. So really, what we want is N times T of X over N times T of Y. Yeah? Okay, cool. So Y has 2N, X, and temperature? T over 3. Huh. So then that's basically 1 over 2/3, yeah? Which is 3/2. Okay? Was that answer B? Excellent. Correct answer is B. Good? All right, one more problem. Temperature for an ideal gas is reduced. Which one of the following statements is true? Which one of the following statements is true? You have 30 seconds. Temperature for an ideal gas, which one of the following statements is true? The molecules collide with the walls of the container less frequently. Molecules collide with each other more frequently. Time of contact between the molecules and the wall is reduced. Time of contact between the molecules is increased. Well, temperature is reduced, so we know that kinetic energy is reduced. So the molecules collide less frequently. Less frequently, because they're just not moving as fast. Okay? Okay, awesome. Last thing I want to mention is another equation you'll see in your data booklet, which is, has to do with energy of gases, is the Boltzmann equation. And basically what it says is average kinetic energy is equal to 3/2 kT or 3/2 RNT. So I have to look at the data booklet. It might have a bar over it in your data booklet, which symbolizes average. Okay, maybe a little bar right there. And what this basically shows you is that the average kinetic energy of the molecules relates to the Kelvin temperature. There's a relationship there, right? K is this constant called Boltzmann's constant. It's in your data booklet. Turns out that Boltzmann constant is the gas constant divided by Avogadro's number. Avogadro's number is 6.02 times 10 to the 23rd. But you don't need to know that necessarily because Boltzmann constant is given to you in the book. Temperature has to be in Kelvin. So this just shows that temperature is proportional to average kinetic energy of the molecules. Okay. What you can do, if there's ever a question about what's the total internal energy of the molecules of a gas, and you're given their temperature, well, if you use either of these two equations to figure out their average kinetic energy in joules, well, then you multiply that by the number of molecules you have, and that will tell you the total internal energy of that gas, right? So you find the average kinetic energy of the molecules, multiply that by the number of molecules, that tells you the total internal energy of the gas, since basically with an ideal gas, we assume that there is no potential energy between the molecules. Whew. Let's go back to where we began. Did we talk about pressure? Did we talk about the equation of state for an ideal gas? Did we talk about the kinetic model of an ideal gas? How about molar mass and the Avogadro constant? Not today, but we did previously. So if we need to review that, let's talk about that. Differences between real gases and ideal gases. This was topic 3.2 in 1 hour. Done. Okay. Holy mackerel. How about these equations? Let's actually look at these equations because we talked about most of them. Pressure equals force over area, PV equals nRT, and the Boltzmann's equations. But look at this one for a second. N equals N over N. We talked about that one previously, I think, in 3.1. What is lowercase n? This is number of moles. Good. What's big N? Number of molecules or number of things, whatever you're trying to figure out how many moles you have. It could be pigs. It could be anything, right? How many moles of pigs do I have? I don't know. So N is the number of things you have. What's N sub A? Avogadro's constant. Great. Awesome. Thanks, you guys.